In this question, we have to show that the series, the sum of numbers added up on the left-hand side equals this expression on the right-hand side. So we're counting up in threes is what we're showing. It's proved by induction. So the first step is always we would sub in the lowest value of n. That the lowest value of n would be n is equal to 1. So on the left-hand side, I've colored this in yellow. So n is equal to 1, we just have 1 is the term there. Or technically it's 3 times 1, take 2. On the right-hand side, if I sub 1 in for n, I end up with 1 over 2 times 3 times 1, take 1. Just evaluating the right-hand side of this, I see it's a half times 2, which is 1. So I've shown that the left-hand side equals the right-hand side. So in other words, it's true when n equals 1. That's always the first step of proof by induction. We prove it for the lowest value of n. The next thing, we're going to assume that it's true for n is equal to k. What that means is that if I was to add up the left-hand side in yellow there, up as far as term k, that means just replacing the n with k. That's the same as on the right-hand side putting k in for n. So it's k over 2 times 3k take 1. I'm assuming that's true. Step 2 is complete now. The next step is I want to prove it to be true for k plus 1. So here I'm going to add up all the terms up as far as k plus 1. I'm going to include that term before it, the k term. And then we have this one extra term we didn't have in our assumption, where I'm putting k plus 1 in instead of n. And that's equal to the right-hand side in pink there if I was to replace n with k plus 1. That's all I've done here. Now I might tidy this up a little bit. So I want to show that this left-hand side equals the right-hand side. The yellow equals the salmon color there. Okay. Now if I look at the yellow part here, you'll notice that what I have in that is the first number of terms up here, up as far as term k. That's the same as we had in the assumption. So I can write that in a different way. I can write up to the k term. I can write that as the sum of that series is k over 2 times 3k minus 1, because we've assumed that to be true. So the left-hand side of our expression here is we have this one extra term, the k plus 1 term. Now I'm going to just neaten this up. I have 3k, and 3 ones are 3, take 2, which is 1. And that equals to the right-hand side. Again, I'm going to neaten up this expression here, 3k, and then I have 3 ones is 3, but take 1, and 3 take 1 is plus 2. Just neatened it up a little bit. So I want to show that these two sides are the same. I want to show that's the aim of the proof. I could start multiplying them out, change both of them to see. The most obvious thing that occurs to me is I notice that there's a fraction number 2 across the way here. So there's a 2 in 2 of the terms, but not in one of the terms. So if I want to make these look a bit the same, I'd need a divide by 2 in the term that doesn't have it, this term here. So to make that being divided by 2, I would multiply it above and below by 2 over 2, which is just 1. So that's a fair thing to do. So now I have an equation where each of the terms has been divided by 2 in the equation. So I could multiply everything by 2. So this is a different expression, but it must be also true. So I'm going to expand what I have here. I have k by 3k and k by 1. And I have then 2 by 3k and 2 by 1. And I have, multiplying out these brackets, I'd have k by the 3k. That's going to be 3k squared. K by the 2, which is plus 2k. The 1 by 3k. And the 1 by 2. Now they're beginning to look alike, so I'm trying to show these are the same. Lastly, you'll notice there's k terms here, a minus k and plus 6k, that's 5k. And then on the other side I have a 2k and a 3k, that's also 5k. So we see that both expressions actually are identical. So yeah, it's true, I've proven what I set out to prove, QED. I've proven that it works for k plus 1. So we write a conclusion, that's the final step. I say it's true for n equals k plus 1 if it is true for n is equal to k. But we know it's true for one value of k, anyway, one value of n, because we've shown it's true for n is equal to 1. So it must be true for 1 and 1 bigger than 1, 2, 3, 4, 5. So it's true for all values. So we've proven it. So I make my conclusion, therefore, that's the 3 dots mean, therefore it's true for all values of n, as long as n is a natural number, n is an element of n. That's the proof.